So now that you've had a chance to kind of understand what the common fork-join pool is doing and see how you can program it, let's talk about a bit more of the internals. So we're going to talk about how the parallel streams framework is mapped onto the common fork-join pool framework. This is actually really cool because it shows you what's happening under the hood. So each worker thread in the common fork-join pool runs in a loop that mostly spends its time looking for something to do. So it's scanning the input, trying to figure out if there's work for it to do. And so we're not going to talk about the common fork-join pool in general, which is what we just showed you earlier in the previous example. We're going to talk about it only in the context of tasks that are associated with the parallel streams framework. You could use the common fork-join pool for other stuff, and because it's common, those would all run in the same thread pool, but that's not what we're going to focus on here. The goal of this design, the goal of the whole common fork-join pool framework, is to keep the worker threads, these guys here in the pool, as busy as possible. We want them to spend all their time computing because that's why they exist. Their purpose in life is to serve at the pleasure of tasks that come from outside. The way this works under the hood is that each worker thread here, each of these platform threads, these Java real threads, or classic threads, has a double-ended queue, which is commonly referred to as a deck, and that serves as the main source of tasks for each worker thread. You can read more about what a double-ended queue here is. It's just a queue where you can insert and remove things at the head or the tail efficiently. And this particular deck is very cleverly implemented using some cool synchronizers we'll talk about in a second. The parallel streams framework will automatically create the fork-join tasks that are run by the worker threads in the common fork-join pool. So you never have to do the same thing we just saw in the previous example where you fork and join and all this stuff. That's done for you by various parts of the framework, in particular the splitterators and the collectors, and other stuff in between, the other parts that are doing the application part. This is what is actually happening under the hood. So if you want to see this source code, at least one variant of the source code, you can take a look at the link at the bottom of the slide. This will give you the abstract task.java source code, which is a superclass used in the streams framework by most of the fork-join tasks to implement the behavior that you would see if you were to run this in parallel streams. So what the abstract task class does is it manages the logic for splitting and for tracking of child tasks and also for producing intermediate results. And this is what it does. So it has a compute method because everything that uses the fork-join task framework uses something that has a compute method is defined on it. It's a recursive task or a fork-join task and so on. And so what we do in this particular case, or what it does in this particular case, is its compute method decides whether to split the task further or to compute it directly, because it's been split to the point where there's no more room for further splitting. It's reached its atomic size. And so what it does here is it has a loop, and it keeps calling on the splitterator that we define here, and it says, please try to split yourself. And it'll keep doing this over and over again until it finally gets a null back. When it gets a null back, it says, OK, uncle, we've split as much as we can split. Now let's do something else. So you can see here we're going to split. We're going to keep trying to split. And what happens is it keeps track of whether or not we've split on the right-hand side or the left-hand side. What does that mean? Whenever you split, you have two halves. One is the left-hand half. One is the right-hand half. And that's called like LS for left side, RS for right side. And so it keeps track of which side we've been forking on. And if we are forking right at the moment, then we change forking right to be false for the next go-around. So we'll fork left next time. And the reason it does that is to try to avoid biased splitterators. We try to give each side a chance to get a chance to run. If you have a splitterator that splits things in half, this isn't really an issue because you could split either side, it wouldn't matter. But sometimes your splitterators are biased. They'll split more on one side and more on the other. A good example would be the linked list splitterator we looked at before. And then after we figure out what task we want to fork, then we go ahead and fork that task. So remember what that does is that goes ahead and sticks that task onto the deck of the calling worker thread in the common fork-join pool, which will either run it or some other thread will come along and steal it. So that's just basically saying, get yourself ready to run in parallel at some point. And then after we are done with that loop, after the loop is finished, after we split things up as much as we possibly can, then the do leaf call is made, and that typically will call for each remaining, which under the hood will call the element sequentially at that point by calling try advance. So what's happening here is that this is splitting things to have them run in parallel. And then when it reaches a point where there's nothing left to be done, then we go ahead and we process the results that are no longer capable of being split any further. So after the abstract task compute method, which we just saw, calls fork on a task, this task is pushed onto the head of its worker thread's deck. So the logic that we just saw here is going to run in some worker thread in the common fork-join pool. And whenever fork is called, it's going to push that task. In other words, down here, when we say tasks to fork.fork, that's going to push the task onto the calling threads, that worker thread's deck. It's work queue, as it's called. And then what will happen is at some point, all the pushing has been done, and then the worker thread will say, okay, now I'm going to do some work. So it'll go ahead and pop whatever's on the top of the stack, and then it'll do its thing, and it'll join the results. So each worker thread processes the contents in its deck in last in, first out order. And hopefully you're all familiar with that. That's what a stack, that's the order of a stack. So things are pushed onto the stack in LIFO, or last in, first out order. And the idea behind that is what's often called fresh work before stale. You want to do the stuff that's on the top of the stack first because it's most likely to have its contents in the cache. So we pop from the head of the deck, and then that task is run to completion. And the reason for doing this is an important thing to remember because it will probably show up on a quiz. Using LIFO ordering improves the locality of reference and cache performance. Again, it's fresh work before stale. If you just put something onto the stack, then if you take it off, it's most likely to have everything in cache memory. So hopefully it'll be a little faster. As I mentioned a couple times before, if an idle thread, like let's say that this particular worker thread has got all of its processing done, rather than going to sleep or busy waiting, what it does is it looks around to the other work queues from other worker threads in the common fork-join pool, and it steals work from them, or tries to steal work from them. If there's nothing to be done at all, it'll eventually go to sleep. But it tries its darndest to avoid going to sleep because it takes a long time to put a thread to sleep and wake it up again. So we'd rather have it do a little bit of extra work to go find more work to keep it busily humming along. And so in this particular case, it will steal the work from the tail of the busy thread's deck. And the reason it steals from the tail is because that way two things happen. Whoops, doesn't really say here, but the reason why it steals from the tail is, number one, the stuff at the tail is probably the bigger elements to be dealt with. So if you steal from the tail, you can then start partitioning a big chunk of things, number one. And number two, it's not going to contend with another thread, the actual owner of that deck, who is taking stuff off of its head. So in steady state, if you have a bunch of items on your deck, then you can take things from the front and from the back without having to contend for a common lock. And in fact, that's another clever thing that's done by the implementation of the deck or the work queue, is they have locking mechanisms that don't have any contention if you steal from the head and steal from the tail, or steal. If you take things from the head and steal from the tail or remove from the tail, and there's other elements in the deck, there's no need to contend for a common lock. So that makes it much more efficient. So there's less overhead of locking in that particular case. So that's the end of the overview of how the common fork-join pool is used by Java parallel streams. We could also talk at length about the common fork-join pool in its own right, but I'm just trying to focus here on what's important for the streams framework.